This is the Innova Engineering hydraulics tutorial. In this video, we're going to run through a hydraulics calculation from start to finish. So we will cover all of the setup and the inputs that you need to run through. We'll run the calculation and then we'll take a look at the results that the program generates. Before we start, I'm just going to remind you of some of the other resources that you can use to get help with the hydraulics calculation. So starting with the help file itself, if you just go to help and then help, this will open up the help file. The help file is broken down into sections based on which tab or which menu you're looking at. So if, for example, you're in the Engineering Parameters tab and you're looking at an input and you can't remember what it does, just go to the Engineering Parameters tab section, pull up the hydraulics parameters, and then you've got an explanation of each input. As well as the help file, in the help menu, we've got the documentation folder. So this has a number of useful guides. The most relevant ones to this video are probably the hydraulics quick start guide, which does the same thing. It just runs through the hydraulics calculation step by step. And we've also got the hole cleaning guide, which runs through the hole cleaning results charts that you get after you run the hydraulics calculation. We also have the tutorial videos page. If you go to playlists and then scroll through the creative playlists, there is one called Innova Engineering Getting Started. And this contains some video clips which will help you through the hydraulics calculation process, such as creating a BHA, setting up your hydraulics, and also looking at charts and reports. In this example, I'm going to be rebuilding the complete example project 3. So if you need to go back and look at any of the inputs that I've put in, you can do so quite easily by just going to File, Open, going to your Innova Engineering install directory, opening the example projects folder, and just selecting example project 3. We want to start with a blank project, so I'm just going to go to File and New. So we'll create our blank project, which I'll now give a name. And a description. And then I'm going to set up the units. So I'm going to go up to the Units menu. I'm going to set our unit set to API units. Then I'm going to tweak the length so that all of our lengths are measured in US feet instead of feet. And then I'm going to save my project. So I'm just going to go up to File and Save As. And I'm going to save this project on my desktop. So I'll just give it a name. And then just hit Save. Now we can start building our drill string. So to do that, I'm going to go down to my drill string table down here, and I'm going to go to the component column, and I'm going to select my first component. In engineering, you always build your drill string from the bottom up. So in a regular drilling BHA, you would start with the bit. I just showed the example that we're building. We're going to start with the bit, then the RSS, and work our way up the BHA until we get to our heavyweights and our drill pipe, which will go back up to surface. Likewise, if you were doing, say, a casing or a liner assembly, you would start with your casing shoe or your seal assembly in the first row, and then the drill pipe that you're running in the liner or the casing in on, that would be the last row. Once we've selected the bit as our first component, we can start filling in information for it. So I'm going to give it a description. Call it the 8.5 inch PC bit. I give it an OD, 8.5, and ID of 3 2/4. If this was a component with a tool joint, like a drill pipe, I can fill in the tool joint OD and ID here as well. I'll give it a weight, and then I'll give it a length. and you can see that the total length automatically updates. And lastly, we have the non-magnetic column, which just lets you signify whether or not the component is made out of non-magnetic material. This is just used for the magnetic interference calculator, which will be covered in the survey correction video. You can see that when I selected a component type in the component column, it also activated this component details box down here. The components details box lets you enter in some extra information for that component, and the information that is available to edit, it depends on the type of component that you picked here up in the component column. So you can see that because I picked a bit, there is some bit specific information like the gauge OD and the TFA that we can enter. So I'm just going to enter in gauge OD of 8.5 inches, and I'm going to edit the TFA. So to edit that, I want to click on this little grey box just here. So bring up the JET details window. So I have a choice here. I can enter in my jets on this side, and this will work out the TFA for me. So I've got 6 12/32 of an inch jets in here, and that has worked out the TFA of 0.6627 square inches. Or alternatively, I can just turn on this fixed TFA checkbox here and just type in the TFA that I want. Next, I'll put in my connection, so 4.5 inch regular, and then I'll select the bit type, which is just PDC. Now that I've filled in my bit details, I want to insert the next component. So I'm just going to select the row with my bit in and click on Insert After, and that will insert a new row. My next component is an RSS, so I'm going to go to my component column and select RSS from the drop-down box. And as you can see, because I've picked a different component type, my component details for this row will be different to the one above. So I could fill in all of my information for my RSS manually like I did with the bit, or alternatively I can use the component catalog. So to access the component catalog, just want to right click on a row and then select from library, and this will open up the component catalog. So the component catalog is just a library of drawstring components which you can select and then insert into your drawstring, which should save some time typing everything out. You can filter the component catalog using these drop-down boxes up here. So you can filter by component type, the OD, the grade if you were looking for jaw pipe or casing, and the nominal weight. If you can't find an entry that suits your needs, you can add in your own by clicking on the Add New button down here. So just as an example, I'm going to add in the RSS that we want to enter into our BHA. So I'm going to enter in the details for the new components. So that is all of the component information and component details for the RSS entered. So I'm just going to click on OK, and that will add in my new component into the catalog. And now we can see our new components listed in the catalog. Using these buttons at the bottom, you can also edit existing entries into the catalog and delete entries as well. And then finally, you have the reset to default option, which will just reset the catalog back to how it was when it was first installed along with engineering. So to insert our RSS into the drawstring, I'm just going to select it and I'm going to click on Insert into Drawstring. And there we go. The information is loaded into the table in the drawstring and also into the component details. There's just a couple of extra component details that aren't stored in the catalog. And that's the RSS done. I can continue building my BHA by selecting my RSS, clicking on Insert After, and then I can start putting in the information for the next component. However, so that you don't have to sit here and watch me fill in the drill string line by line, I'm going to import the rest of the drill string that I need. To do this, I'm going to use the Import and Export BHA functions in the File menu. So while you're in the drill string tab, you just go to File and go to Export BHA, and this will export the BHA that you have in your table and any associated component details with those components. So you just want to save your BHA file. It's going to save mine to the desktop, and it will save it as a .bha file. And to import in a BHA, you just want to have the drill string tab open, then go up to File and Import BHA, and locate a previously exported BHA file. So this is one that I created earlier by exporting the BHA out from example 3. So I'm just going to import it back into our project now by selecting it and then hitting open. And that has imported the whole of our drill string, including all of the component details associated with each row. So you can see in the BHA that we've imported, the last line, the drill pipe, has a length of 24,608 feet, which is enough to go from the top of the BHA all the way back up to surface. You're not required to do this. You can just put in, say, one joint length of your final drill pipe, and then when the calculation runs, it'll just repeat this last row over and over again until it's long enough that it stretches all the way back up to surface. However, if you do want to put in the full length of your drill pipe so that it looks better on, say, on reports, then you can use this adjust length button down here to work out how long this drill pipe needs to be. So to use the adjust length button, we need to go to our engineering parameters and set our calculation depth. The calculation depth is essentially where you want your bit to be when you run the calculation. So in this case, it's going to be at the bottom of the 8.5 inch section, which in this well is 24,845 US feet. Now we can go back to the drill string tab, and we want to select our drill pipe and then hit the adjust length button. What the adjust length button does is that it takes the component you have selected and it increases the length until the total length of your whole drill string is the same as the calculation depth that you set. Just above the component details section, we have a result here for the weight of our BHA. This is the Boyd weight, so it depends on the mud weight that we've set, and we set the mud weight over on the right hand side in the fluid properties section. So I'm just going to set my mud weight to 9.3 pounds per gallon, and you see that's changed the BHA weight. At the moment, this BHA weight is measuring all of our components, including all of this 24,000 feet of drill pipe, and this is because we haven't set where the last BHA item is. So if I toggle this on, let's set my last BHA item to my final stabilizer, so item 8, we now get a more accurate result for our BHA weight. If we have a jar in our assembly, we'll also get a result here for the weight below the jar. So I will just add one in now as an example. There we go. So now that we've got a jar component in our drill string, you can see that we now get a result for the weight below the jar as well. Now that we've completed our BHA, we can generate a BHA report. To do that, we go up to the File menu and select Print BHA. But before I do that, I'm going to go to the option above and select Print Reports. This brings up the Report Manager, which is normally used for printing off your results reports. but it also has the option to select a logo and a secondary logo to put on your reports. And any logo that you choose here will appear on all of your reports, including your BHA report. So to select your primary and secondary logos, you use these two buttons up here. And then to clear your primary logo and your secondary logo, you use these two buttons. So I'm going to select a primary logo. The only format of image that engineering accepts is the .bmp type file. I've got the Innova logo saved on my desktop, so I'm just going to select this one. And that's the logo assigned. And I can close my reports manager, go back up to File and select Print BHA. This brings up the Print BHA window where you can fill in some extra details that will appear at the top of the report. I'm just going to fill these in now. So we start with the operator, the well, field, the rig. We've got the BHA number, the bit number, the depth in, and the depth out at the end of the 8.5 inch section, the date in, the date out, number of drilling hours, the bit grading in, the bit grading out. And we can also put in the survey offset and the gamma offset. And then if you have other survey tools in there, you can set the offsets for those as well. The fill color option lets you pick the background color for your table headers. So I'm just going to leave that as pale blue. Then we have the print inverted option down here. So if you leave this unchecked, then the BHA report will be printed as you see it in the drawstring tab. So it'll have the bit at the top and then work its way down to the draw pipe at the bottom. If you select print inverted, then this order will flip and you'll have your drill pipe at the top and your bit at the bottom. I'll leave this unchecked and then I just hit print. And this will generate an Excel format BHA report. So at the top of the BHA report, we have the information that we just filled in. We have the total BHA weight just up here. Then you have the listing of the BHA components. And then at the bottom, we have some extra information taken from the component details box for some of the components. As I click through each of these rows in our BHA, you can see that not all of the component details fields have been filled in. This is because not all of the component details fields are relevant for the hydraulics calculation. Some of them are used just in torque and drag, and some of them aren't used in any calculations at all and just appear on reports. To check which of the component details are relevant to the calculation that you're doing, you can use the help file. So I'm just going to go up to help and then help. And then you want to look in Appendix E. Appendix E lists the component details fields for every component type, and it will tell you which calculation, if any, the component detail is used in. If a component detail is used in hydraulics or torque and drag, it will tell you, and in a couple of places it says that the component is used in engineering, which means it is used in multiple calculations. So I will just run through a few of the component details that are most important to the hydraulics calculation, starting with the bit. The TFA obviously is very important. RSS type components, MWD type components, and motor type components all have a pressure drop field, which is important to include to make sure that you get an accurate result when modeling these types of components. Motor type components also have a differential pressure field, which should be included when running hydraulics calculations. Stabilizer type components also need to have the details for their stabilizer blades filled in, as these affect both torque and drag and hydraulics calculations. So in the drawstring box up here, you would fill in the body OD of the stabilizer, and then you would fill in the OD of the stabilizer included in its blades in the component details. You would also fill in the stabilizer blade length, blade width, and number of blades. RSS type components, MWD type components, and motor type components also have information where you can put in stabilizer details if there are stabilizers attached to those components, such as a stabilizer sleeve added onto a motor. As for the main drill string table, obviously the OD and the ID and the length of the components is very important in the hydraulics calculation, as well as the tool joint ODs and IDs on your drill pipes. The weight of the components is not actually used in the hydraulics calculation, just in torque and drag and sag calculations. By far the most important component in your drill string is going to be your drill pipe that leads back up to surface. This is because it makes up the vast majority of the drill string that is in the hole when the calculation is run. In the case of this example, it's actually 99% of our drill string. So any errors or inaccuracies when filling in the information for the drill pipe that leads back up to surface can have a major effect on the result of the hydraulics calculation. So now that we've finished building our drill string, we can move on to the weld geometry section, which is this section in the top right up here. The weld geometry section is where we define the diameter of the weld bore from surface down to the bottom of the section that we are running the calculation for. You build it from surface down, so I'm going to start with a 9 5/8 casing, which runs from surface to the top of the 8.5 inch section. So to do that, I'm going to open up the type drop-down box and pick casing. I'm going to enter in my measure depth for my casing shoe. If we already had our survey set up in the survey tab, then the program would automatically calculate the TVD for the casing shoe as well. And then I'm going to enter in my OD for my casing, which is 9 5/8, and my ID. Next we have the open hole section, and in this example we actually have a section of 8 7/8 open hole before we get down to the 8.5 inch open hole section. So I'm going to pick open hole, set my measure depth of the bottom of this section, then fill in the ID and the OD. And when you fill in an ID or an OD for an open hole section, the program automatically fills in the other entry. So next is my 8.5 inch open hole section. And I've put in my measure depth for the bottom of the 8.5 inch section. You only need to worry about the parts of the weld bore that the drill string and the drilling fluid are actually exposed to. So in this example, my 9 5/8 casing runs from surface down to the top of the open hole section. I could have other casings in the well as well, but because they're sealed away behind the 9 5/8 casing, I don't need to enter them into the weld geometry table. Once you've entered in your weld geometry, you can have a look at the weld geometry schematic by going up to Tools and selecting Weld Schematic. This is a fairly simple example of just a well drilled on land. But we have other options in the type drop-down box for other types of wells. If you were drilling offshore and using a visor, your weld geometry would look like this. So you'd insert a visor at the top before the casing and the open hole sections. And if you were drilling visorless, then the weld geometry would look like this, with an air gap at the top and then open water and then your case and open hole sections. Now we move on to the fluid properties section. This is where we define the drilling fluid that is in our well bore. So we enter the mud weight here, which we entered in earlier. So just 9.3 pounds per gallon in this example. Then we can enter in our PV and our YP. When you enter the PV and YP values, the program automatically calculates the N and K values for the mud. However, if you don't have PV and YP values entered, then you can also use the 600 and 300 viscometer readings to calculate the N and K as well. When you run the hydraulics calculation, you've got a choice of 4 different hydraulics models. So we've got access to Bingham, Power Law, Herschel-Bulkley and Robertson-Stiff models. If you're using the Bingham model, then you only need to enter the mud weight, the PV and the YP in order to run the calculation. But if you're using any of the other models, you also need to enter in your viscometer readings. You can enter in your mud values manually, or you can use the fluid library, which you can access by clicking on this button just here. This opens up the fluids library window. As you can see, we've got some generic MUDs that come pre-installed with engineering. If we want to, we can add our own MUD to the library. We can do that just by clicking on the Add New button down at the bottom left. This will add in a new row, which we can then fill with our MUD information. So I'm going to fill in the MUD for example. And just put in whatever information you have. And then hit apply. That will save the changes. When you select a fluid in the table, it displays the shear stress versus shear rate chart for that fluid, and on it you can see the predicted performance of your MUD based on the different hydraulics models that we have available. The crosses on the chart represent your viscometer readings. So if you have those readings available, you can use this chart as a guide for selecting the best hydraulics model to run for your fluid. So now that we've got our fluid into the fluids library, I can just close this down, and then I can pick it from this drop-down box here. So I'll just clear out all of my readings, and then pick it from the drop-down box, and it will automatically populate with my readings from the fluids library. Below the main fluid properties section, we have the cuttings details section. These cuttings values are required to get results for hole cleaning when you run the hydraulics calculation. These are the default values here, and if you want to change them, you can make them editable by clicking on these checkboxes, and then you can edit them with whichever values you want. And then finally, we have the additional fluids section. So if you enable it, you can enter in some additional fluids. These would be like pills or sweeps. So you would enter in the volume of the fluid in barrels, in this case, and the density in pounds per gallon. And then what the program does is it uses the values that you've entered to work out a new average mud weight for the whole wellbore. For this example, I'm just going to leave the cuttings as their default values, and I won't use any additional fluids. So that concludes the drill string, weld geometry and fluids tab. We're now ready to move on to the surveys tab. In engineering, you have 3 different types of surveys, which you can access through this survey selection drop-down box just here. So you've got actual surveys, well-planned surveys, and raw surveys, and in each engineering project file, you can store one of each. So raw surveys are constructed by entering in a measured depth and then the accelerometer and magnetometer readings from your survey tool, and then engineering will work out your inclination and azimuth for you. The raw surveys are used just for survey correction. They can't be used in hydraulics or torque and drag calculations, so I'm not going to go any further into the raw surveys. The other 2 types we have are actual surveys and well-planned surveys. These both work in exactly the same way. You just enter in a measured depth, an inclination, and an azimuth for each survey point or plan point. There are 3 ways to enter in survey information into engineering. The first one is just manually, so I can just type in my surveys, starting with my tie-on point, and then my first survey. And so on. The second way of getting information in is by copying and pasting. So if you have your survey data in a table format, such as say an Excel spreadsheet, then you can copy and paste this information straight in from the table into engineering. So I'm just going to select my actual surveys in Excel, copy, go back into engineering, and then just right click on the row that I want to start at and select paste. And that will paste in all of my surveys. And the third way of entering surveys is to use the import survey function. So I'll switch to my well plan list, and then I'll go to File and I'll select Import Survey. Engineering will ask you to locate the survey file that you're importing. Engineering can handle a number of different file types, so we've got tab delimited text files, space delimited text files, comma delimited.csv files, Excel files, navigator short color correction text files, and LAS files. The file that I'm using is a tab delimited text file, so I'll select tab delimited, I'll select my file and I'll click on open. This brings up the import survey window. So you can see in the bottom portion of the window, we've got all of the surveys that we're going to pull in. And then at the top, we tell the program which rows and which columns we want to pull the data from. So here we set our starting row and our ending row. Our starting row is row 2, so that will cut off the headers. And then our ending row is 269. And then here we set which column represents which type of data. So we've got a choice between measure depth, inclination, azimuth, and not applicable. In this case, my data is already in the correct columns, so I've got measure depth first, inclination in the second column, and azimuth in the third column. And now I can just click on import. You'll get a warning saying that this will overwrite any data that you already have in your surveys. That's okay, we've got no data in at the moment, so I can just hit OK. And there we go, that's our survey information imported in. In your weld plan and actual surveys, you only enter in your measure depth, inclination, and azimuth, and then the program will work out your TVD north-south, east-west, and vertical section automatically. The only place you can edit those are in your tie on line at the top. You can see in the weld plan surveys that we just imported in, there are some sections that are perfectly straight. So we've got a perfectly straight section here, a perfectly vertical section here, and then we've got a perfectly horizontal section down here. Obviously, in real life, it's impossible to drill a perfectly smooth weld bore. So in order to make our results from our calculation a bit more realistic, we can add some tortuosity to our surveys. In order to do that, we just click on the tortuosity button down here in the bottom row. So what the tortuosity tool does is it adds or subtracts a tiny amount of inclination or azimuth to all of our surveys, that way getting rid of any completely straight sections. To turn it on, just click on this Apply Tortuosity checkmark box, and that lets you set your options. So you have a choice between sinusoidal or random tortuosity. Random just applies the inclination and azimuth in a random direction, whereas sinusoidal will apply it so that the additions and the subtractions form a sine wave. The tortuosity is applied in a repeating pattern, and you can set how long this pattern is using this period length here. By default, it's 25 feet. You have a depth range option here. If you leave this off, then it'll apply tortuosity to the entire set of surveys. If you turn it on, you can specify where you want to start applying tortuosity and where you want to stop. I'll leave this turned off. I'll leave the period length as the default 25, and I'll set it to random, and I'll hit OK, and that applies tortuosity to my surveys. You won't actually see the tortuosity applied to the inclination and azimuth that you've entered into your surveys, but you can see it in the calculated survey data, which you access down here. But before we can access it, we need to go to our Engineering Parameters tab and make sure that Engineering is actually using our weld plan surveys for its calculations. So I'm just going to select Weld Plan from the drop-down box, and I can go back to my Surveys tab, and I can click on Calculated Survey Data. So Engineering does not actually use the surveys that you've entered into your survey listing. Instead, it takes those surveys and any tortuosity that you've applied and generates an interpolated survey listing. The main reason it does this is so that there's a nice consistent interval between each survey station. But if we scroll down to an area that was previously completely straight, we'll see that there's been some tortuosity applied. So there's just a very small addition or subtraction to the inclination and the azimuth. So after you've entered your surveys, you can view them by going up to the Plots menu. So to view a survey, just have it open in your Survey tab and then go up to Plots. and you can select a section view, a plan view, or a 3D view. At the top of the Surveys tab, we have these other three sections: the vertical section, the raw survey data section, and the survey corrections section. The vertical section just lets you set your azimuth and your north-south and east-west origin of your vertical section. That doesn't affect any calculations. It just affects how the vertical section is calculated in the vertical section column, and also how your section view plot is calculated. The raw survey data and survey correction sections are just used in survey correction. They're not used in hydraulics or torque and drag calculations, so we're not going to cover them here. So with the surveys filled in, we can now move to our Engineering Parameters tab. The Engineering Parameters tab is split into 5 sections. On the right-hand side, we've got a hydraulics results section and a hook load and torque data results section. These two will fill in automatically when we run the calculation. And then on the left, we've got a hydraulics setup section, a survey selection section, and then a torque and drag setup section. Torque and drag setup only refers to the torque and drag calculation, so we're not going to worry about it in this video. We're going to focus on the hydraulics setup and the survey selection. So starting from the top, we've got the hydraulics model. You can pick which model you want here out of the 4 that are available. I'm just going to stick with Bingham. The next one is surge and swab. You can choose whether or not you measure your surge and swab using an open-ended or a closed-ended drill string. If you are using a ported float in your drill string, you would select open-ended, and a non-ported float, you would choose closed-ended. We're going to go for closed-ended in this example. Next one down is where you set your surge and swab reference. This sets where your surge and swab results are going to be measured from. So you've got a choice between the bit, the casing shoe, or the bottom of the hole. You can also check this checkbox, and you can set a user-defined depth for your surge and swab reference. We're just going to leave it as the default as the bit. Next, we've got the ROP. So this sets your ROP while you're drilling, and it affects your ECD and your hole cleaning results. I could set this as 150. Next, we've got the RPM of your drill string. This will add some additional pressure to the results based on your RPM. Let's set that to 100 for this example. Next is the ECD adjustment. And what you can do here is you could put in a negative or a positive value, and it will shift all of your ECD results one way or the other. You'd normally do this if you were trying to match your ECD results to another curve, like say some MWD pressure while drilling data. But we are just going to leave this as the default as 0. The next one down, SWDen stands for saltwater density. So if you are doing riserless drilling, you need to include the density of seawater in your calculations, and this is where you would fill it in. The default is 8.55 pounds per gallon. We don't need to worry about this, so we can just leave it as the default. Next one down is surface pressure losses. This is to cover losses in your standpipe pressure as the mud flows through your surface pipes. We're going to enter in a value of 100 psi for this example. Next is the calculation depth. So the calculation depth sets where your bit is when you run the calculation. You can enter the value manually, or you can go down to the survey selection section and use one of these 2 buttons. So last survey depth will set your calculation depth to your deepest survey depth, and last geo depth will set your calculation depth to the deepest depth in your wellbore geometry on the drill string tab. So I'm just going to select last geo depth, and that will set our calculation depth to the bottom of our hole section. And then we can move down to the flow rates and the tripping speed section. So flow rates is the pump rate of your mud, and the tripping speed is your speed tripping in and out of the hole. So there are 2 ways of filling in these tables. If you put a value in the middle field, and the program will automatically generate some other values above and below it. Or alternatively, you can select this manual flow increment or manual tripping increment checkbox down below. So if I do that for the flow rates, and then you can manually enter in as many different flow rates or tripping speeds as you want. So I'm going to fill in my flow rates table manually, but leave my tripping speed is automatically filled in. And then the last thing we need to do is just set our survey selection. So this is telling the program which of our surveys we want to use. We can choose whether or not to use our actual surveys. So that'll be these surveys in our survey tab, or our well plan surveys. So these surveys, which we applied some tortuosity to. The other option is a composite listing, which just combines those two surveys together into one survey listing. We are going to choose the well plan. So now that we've entered our parameters, the last thing that we need to do before running the calculation is to check our options. And we can do that by going up to the options menu up here. The options menu lets you tweak how the calculation runs. There's a bunch of different options in here, and not all of them are relevant to hydraulics. So I'm just going to go over the ones that are. So at the top, you've got the include tool joints and include stabilizers and centralizers options. These are on by default, but if you toggle them off, this will remove your tool joints and your stabilizers from your hydraulics or your torque and drag calculations. You've got the survey calculation method. This just sets how the program interpolates between your survey points that you've entered into the survey tab. I always just leave this as the default minimum curvature. And then you've got the hydraulics model options down here. Most of these cover surge and swab results. At the top, we've got surge and swab parameters. So if I click on this, this will open up the surge and swab parameters box. In the surge and swab parameters window, you can set the defaults for the mud compressibility, the gel strength, and the stand length. If you're using feet or US feet, then your default stand length will be 100. If you're using meters, then the stand length default is 30 meters. I'm just going to leave these as the default. Then we have surge and swab include pipe acceleration. If you turn this on, then each stand will have an acceleration and a deceleration stage in between the tripping speed that you set. If you leave this off, then the pipe will move at constant tripping speed. The next one is include gel strength pressure loss. So you can turn this on to include the extra pressure required to break down gels in the mud. Normally this is very small. The next one is continuous circulation. So when this is off, the circulation will stop and start as if it was a drill rig making connections. If you turn this on, it'll behave more like coiled tubing with a continuous flow. So if you were using coiled tubing, you would turn this on. A limit acceleration effects just sets a maximum value for the surge pressures that you get due to acceleration. This is to stop very large artificial equivalent mud weights being generated at shallow depths. Continuous tripping, again, you would turn this on if you were modeling coiled tubing. When this is on, you have one acceleration phase at the beginning and one deceleration phase at the end, as opposed to having your tripping stopping and starting as if you were a drill rig making connections. Use bit TFA for open-ended calcs. So if you have surge and swab set to open-ended in your hydraulics engineering parameters and then turn this on, engineering will use the bit TFA to work out surge and swab calculations. When this is turned off, engineering will use the ID of the last component. Pump pressure safety factor. If you select this, it'll open up the pump pressure safety factor window. And what you can do here is you can increase all of your standpipe pressure results after running the calculation by the percentage that you put in here. So you can use this to add in a safety factor to your standpipe pressure results. MPD data. So MPD stands for Managed Pressure Drilling. So if you're running a managed pressure drilling operation, you can enter in the back pressure exerted in this box here, and this will be added to all of your standpipe pressure calculations and also be reflected in your ECD results. And then down here we have an effective mud weight calculator. So you can put in the desired effective mud weight increase and your TVD, and the calculator will tell you how much back pressure you want to enter into here in order to achieve that desired effective mud weight increase. And then lastly, we've got a visor boost rate option. So if you were boosting the flow rates through your visor, you can enter it here, and then this will affect the annular pressure loss, the annular velocity, your hole cleaning, and your ECDs in the visor. Obviously, this only works if you've entered a visor into your weld geometry in the drill string tab. If you forget what any of these options do, the best place to remind yourself is the help file. So go up to help. That will bring up the help file, and then go to menus and the options menu, and all of your options are there. Okay, so we've entered all of the required information into our drill string, weld geometry and fluids tab, into our survey tab, and we've set up our engineering parameters and picked all the options that we want. We're now ready to run the calculation, and we can do that by going up to the calculate menu here and just selecting hydraulics. And once the calculation is finished, you should see this window saying hydraulics calculation complete. Once you run the hydraulics calculation, the hydraulics results section of the engineering parameters tab will be populated with some initial results tables. Up in the top left, we have a table that details all the pressure losses in the system. So we have the surface losses that we inputted into the hydraulic setup just here. And then we've got the pressure losses and motor differential pressure loss that we specified in the drill string tab. And then in the top line, we have the pressure loss through the bit and some bit performance results. So we've got hydraulic horsepower per square inch, jet velocity, and impact force. On the right-hand side, we have results for standpipe pressure, total annular pressure loss, the clean ECD, and the dirty ECD. And this table gives a result for every flow rate that we entered into the flow rates table in the hydraulic setup. And then this bottom table breaks down the pressure losses and their flow regime for each of the drill string components that we entered into the drill string tab. You have a line for each component, and the next column will detail the hole section that they're in, so either cased or open hole. You can see at the top that the drill pipe is repeated 3 times. This is because the drill pipe is present in all 3 of our hole sections that we set up in the weld geometry. So it's in the case section, it's in the first 8 3/4 inch open hole section, and then it's also present in the 8.5 inch open hole section. Next, we have the pipe pressure loss and annular pressure loss columns. So these will just give you the pressure losses internally inside the pipe and then externally in the annulus around each component. And you've got the annular velocity of the mud around each component. You've got the flow regime in the annulus, so that'll be LAM for laminar and TUR for turbulent. And you've got the cuttings percentage, so this is what percentage of the mud in the annulus is made up of cuttings. Then you've got CCI, which stands for the Cuttings Cleaning Index. And then you've got a top and a bottom column, which gives you the measured depth of the top and the bottom of each component in the hole. So this top left table and this bottom table both depend on the flow that you've selected from this drop-down box at the top. So when you open up this drop-down box, it'll have the different flow rates that you set in the hydraulics parameters on the left over here. And when you pick one of these, the top and bottom tables will change to reflect the results for that flow rate. Some results tables in the reports are also dependent on the flow rate that you pick here. So for example, I'll just pull up the hydraulics summary. And you can see here there's a table for pressure loss information, and it's for 500 GPM. This is because when I created the hydraulic summary, I had 500 GPM selected in my flow from this drop-down box. If you want to, you can quickly export these tables out by left-clicking in the top left of each table here, pressing Ctrl+C to copy, and then you can paste them into another document, like say an Excel spreadsheet. However, you'll see when we come to do reports that there are options to include all three of these tables properly in your reports. All of the other hydraulics results are available from the hydraulics results menu at the top. And this is where you have access to your hydraulics results charts. The hydraulics results charts are split into two categories, hydraulics charts and hole cleaning charts. And this is because the hole cleaning charts are all snapshot charts. And I will explain what a snapshot chart is in a moment. So for our hydraulics charts, we have a pump pressure chart. The pump pressure chart will tell you the standpipe pressure that you expect to see at surface depending on the depth of your bit. And you have a line displayed for each of the flow rates that you entered into your engineering parameters tab. Next, we have the ECD chart. So on the ECD chart, we have three different types of result. We've got the clean ECD, the dirty ECD, and the ECD snapshot. I'll explain the clean and dirty ECD first, so I'm just going to clear out the ECD snapshot from the chart. So for clean and dirty ECD, your depth represents the depth of your bit, and then where it intersects with a line will give you the effective circulating density in the annulus at the bit. The clean ECD value represents the mud without any cuttings in it, and the dirty ECD value represents mud that is loaded up with cuttings. The volume of cuttings for your dirty ECD is based on the ROP that you entered into the engineering parameters tab. So if you have an ROP of 0, then the clean and dirty ECD will be the same here. And then you've got a line for each of your different flow rates that you entered into the engineering parameters. The third type of line that we have in the ECD chart is the ECD snapshot. And I'm just going to clear out everything apart from one flow rate for a clean ECD and an ECD snapshot, just to make it clearer what's going on. So when we call something a snapshot in engineering, it changes how we read our depth on our y-axis. In a normal non-snapshot chart, the depth on the y-axis represents where the bit is. But in a snapshot chart, the bit stays at the calculation depth that you specified in the engineering parameters tab. And the depth that you read off the y-axis represents, in this case, the ECD at that measured depth in the well bore. So for example here, at 10,000 US feet, the clean ECD is telling you the clean ECD at the bit when the bit is at 10,000 feet. But for the ECD snapshot, the bit stays down at our calculation depth, just shy of 25,000 feet. And 10,000 feet would represent the ECD in the annulus at 10,000 feet measured depth. So that would be the annulus around the drill pipe. The ECD snapshot represents a cuttings-free annulus. So down at the calculation depth, when the bit depth for the normal chart and the snapshot chart is the same, the ECD snapshot and the clean ECD will give you the same value. And of course, there is also a snapshot line for every flow rate that you've entered into your engineering parameters tab. And then the final line in the chart is just the mud weight, which is a constant we set in the drill string tab. The last chart in the hydraulics chart is the surge and swab chart. So in the surge and swab chart, the depth on your y-axis represents the depth of the bit, and these blue and red lines represent the effective mud weight created by either the surge or the swab generated when you're tripping in and out. These blue lines represent the swab, and these red lines represent the surge, and you have one of each line for each of the tripping speeds that you entered into the Engineering Parameters tab. And then this line down the middle is your mud weights that you entered into the drill string tab. Where these surge and swab values are being measured depends on where you chose for your surge and swab reference. So you can see in the title that our reference is the bit, which we set in our Engineering Parameters tab just here. Surge and swab reference, we just left it as a default for the bit. But if you set your reference to somewhere else, like say the casing shoe, then these depth values would still represent the depth of the bit, but the effective mud weight values that were generated by the chart would show the effective mud weight at your reference, which would be the casing shoe in that case. Next, we have the hole cleaning charts. First up is the annular velocity profile chart. And like I said before, all of these hole cleaning charts are snapshot charts, which means that the bit stays at the calculation depth. And you can actually see in the title, it tells you the depth of the bit. And so the depth value on the y-axis here represents the measured depth in the hole. So the annular velocity chart just tells you the speed of the mud in the annulus at that measured depth in the hole, while the bit is down at the calculation depth. And if we toggle on our casing, you can actually see how the annular velocity changes in the different hole sizes. And once again, you've got a line for each of the flow rates that you entered into your Engineering Parameters tab. So next we have the CCI profile chart. CCI stands for Cuttings Carrying Index. Again, you've got a line for each of the flow rates that you entered into your Engineering Parameters tab. And then for the measure depth that you read off your depth axis, this chart will tell you what the cuttings carrying index is for that flow rate at that measured depth when the bit is down at the calculation depth, which you can see in the title of the chart. Next, we have the cuttings percent chart. So the cuttings percent just tells you how much of the annulus at that point is made up of cuttings. So again, you just read off your depth, pick the line for the flow rate that you want, and that will tell you the cuttings percentage of the mud in the annulus at that measured depth when the bit is down at the calculation depth. The cuttings percent is affected by the ROP and the RPM that you entered into your engineering parameters, so those are included in the title of the chart as well. And then lastly, we've got the minimum flow rate chart. So in the minimum flow rate chart, each of these lines represents a different ROP. The smallest ROP will be the ROP that you entered into the Engineering Parameters tab. So in this case, 150 US feet per hour. And then the program will automatically generate 4 other ROPs. To interpret this chart, you want to find the maximum value for the flow rate for your chosen ROP. So just to make this easier to read, I'm going to clear out all of the other ROPs, apart from the ROP that we set in the engineering parameters, 150 US feet per hour. And then I want to find the maximum flow rate. So that's just here. So this is the flow rate that I require in order to clean the hole while drilling at 150 feet per hour. So those are all of the hydraulics results charts. The next 4 options, pump pressure data, ECD data, surge and swab data, and minimum flow rate data, are all data tables that contain the data used to generate these charts up here. So if, for example, I open up the pump pressure data, this gives me a table with my depth and then a standpipe pressure result for each of my flow rates that I entered into the engineering parameters. So these are the values that were used to populate the pump pressure chart. If I want to, I can export this table by going up to File and Export. And this will let me save my table either as a text file or an Excel file. We have the survey data option. So this can only be accessed when I'm looking in the surveys tab. And this just opens up my calculated survey data table again. This is just to show you the surveys that the program used to generate the hydraulics results. And again, I can export this table by going up to File and Export. And lastly, we have the hydraulics summary. So selecting hydraulics summary will generate a PDF report that contains a summary of your hydraulics inputs and results, and also a couple of charts. At the top here, we've got our project name and description, and then we've got the inputs that we entered into our drill string tab, our engineering parameters, and the options that we picked from the options menu. Next, we have some results tables. So we've got some pressure loss results for 500 gallons per minute flow rate, and you can change that flow rate by changing the flow rate from this drop-down box before you select hydraulic summary from the menu. And you've got a hydraulic summary table, so for each of our flow rates that we selected in the engineering parameters, it gives you results for standpipe pressure, annular pressure loss, your clean ECD, your dirty ECD, your pressure loss at the bit, your bit hydraulic horsepower, your bit hydraulic horsepower per square inch, and your jet velocity. Then there's a drill string summary, which is just a printout of the drill string that we created in the drill string tab. And then you've got a hydraulic snapshot table. And this table is just a printout of this results table here. It corresponds again to the flow rate that you picked, and also to your calculation depth that you ran the hydraulics calculation for. And then lastly, you have your pump pressure chart and your ECD chart. So the hydraulics summary is designed to just be a way to quickly generate a report with one click, but it's not customizable. If you want to customize what goes into your report, you can do so by going to File and Print Reports, and this will bring up the report manager. I will go into much more detail over what all of the options in the reports manager do in the charts and reports video. But for now, I'm just going to give a demonstration of how I can use the report manager to customize a hydraulics report. So I can pick whether or not I want to print my report in a PDF format or an Excel format. I'll choose PDF. I can customize some things like whether or not I want to include a cover page or a header and a footer. And then I can come down to this bottom section and I can pick from these tabs which type of report I want to create. In this case, I want to pick the first tab because we're creating a hydraulics report. And then I can pick and choose which inputs and outputs tables and which charts I want to go into my report. So in this example, I will just toggle off a few things that I don't want, but I'll leave in all the charts. And then I just click on this printer icon to print my report. And then you can see I've got my inputs and my summary tables, just like I had in the hydraulic summary, but I've also got all of my charts. Before we conclude this video, there's just one last thing to point out. If you change any of your inputs, so any of your inputs in your engineering parameters, your surveys, or your drill string tab, then you need to go up to the calculate menu and run the calculation again before any of these changes will be reflected in your results or in your charts and your reports. That concludes the hydraulics tutorial, so we'll now move on to the questions and answers section. After each of these questions, give the video a pause and see if you can answer them yourself before you view the answer. So first up, where do I enter the bit TFA? The answer is in the component properties details when the bit is selected. So you select your bit in the drill string table, and then you should see in the component details section at the bottom the option to change your TFA. Next, I have multiple casing strings in my well. Which one do I enter into the well geometry? The answer is only the casing strings that are exposed to the annulus. So in the example that we use in this video, the 9 5/8 casing stretched from surface down to the top of the open hole section. We could have had other casings that were cemented in before the 9 5/8, but because they are now sealed behind the 9 5/8 casing and they're not exposed to the annulus, we don't need to worry about them. We just needed to enter the 9 5/8 casing. Next, what is the most important component in the drill string? The answer is the drill pipe, specifically the drill pipe that stretches from the top of your BHA back up to surface, as this is the component that will occupy by far the most of the weld bore. So any inaccuracies in the details that you enter for the drill pipe will have a major effect on your results. Next, what is the difference between a normal chart and a snapshot chart? In a normal chart, the depth represents the position of the bit or the casing shoe if you are running casing. While in a snapshot chart, the bit stays at the calculation depth that we specified in the engineering parameters, and the depth on your chart represents the measured depth in the weld bore. And finally, where should I check if I can't remember what an input parameter does? The best place to look is to look up that parameter in the help file, but the Hydraulics Quick Start Guide and the online video tutorials are also useful. That concludes the question and answer section, so we'll now move on to the exercise section. So in this exercise, you're going to set up and run a hydraulics calculation from scratch. You can either copy one of the existing example projects, or you can make up your own inputs. The point here isn't necessarily to get realistic results, it's just to get you used to the process. So start off by creating a new engineering project and set your units, and then start building your drill string. Try building your drill string by inserting items from the component catalog. Alternatively, you could export a BHA from one of the example projects and then import that BHA into your project. Whichever method you use, remember to check that all of the important component details for the hydraulics calculation have been filled in your drill string. Then create a weld geometry in the weld geometry section and fill in your mud properties in the fluid properties section. Then move on to the surveys tab and enter in some surveys. Again, if you want to, you can copy some existing surveys over from one of the example projects. Once you've got some surveys into your survey tab, use the tortuosity tool to add some tortuosity to your surveys. Then you can move on to the engineering parameters tab and you can fill in your hydraulics parameters. Then go to the options menu and just review which options you have selected. Then you can run the calculation and look at some of the results charts in the hydraulics results menu. Once you're happy with your results, you can print off a hydraulics summary from the hydraulics results menu. If at any point you become stuck, refer back to the video for a refresher. Thanks for watching. If you have any further questions, you can get in contact with us via our support or our sales emails.